Hello, my name is Evan Hennis, and this video will cover a project I created demonstrates linear programming using the game Rock, Paper, Scissors as an example. Now, I'm going to walk through my Jupyter notebook of linear programming using rock, paper, and scissors. I originally did this back in summer of 2017 when I had a reinforcement learning class. I needed to replicate some data in a paper, and it used linear programming, and they cited an example of the rock, paper, scissors application. They never showed how to do it, and it was slightly harder than what I had seen in our textbook, so I wanted to expand on that and basically write this out so I get it straight in my head, and then I could take this and go to the much more complex linear programming assignment I had to actually do. So I figured this would be a good video to make. First off, CVX opt is the open source package I used. It was supposed to be a lot faster than the default package, so I downloaded it, ran it, and it turns out since I was using Windows there wasn't much speed up, but I still used it just to make it consistent with everybody else. And the installation instructions are pretty simple. It's a pip install. So the first thing I gotta do is just load the package. And in this package there's a solver class, and that requires the matrices C, G, and H, and that's based on the C transpose X. That's what you have to minimize, subject to G times X plus your cushion equals H, AX equals B, and S is greater than 0. The C matrix is what I need to minimize, so for that I had to put -1 for U to make sure I minimized, with R, P, and S mean rock, paper, scissors. The G matrix is where everything comes together. This is where you take all of your equations and make the requirement of your program. The first 3 equations are just throwing rock, paper, scissors. If you throw rock, you lose to paper, you win to scissors. So you have 1 in the U column, 0 in rock, -1 in P, and +1 in scissors. Same thing with paper and scissors. Papers beat rock, loses scissors. So you have the 1 in rock, -1 in scissors. Scissors, you lose to rock, so you get the -1. You beat paper, you have 1 there. And one thing we'll touch on later is less than or equal to 0. This will go into the H matrix, which I'll show in a second. The next 3 rows are just making sure you end after the first round. And with the library I used, you can't do R is greater than 0. You need the -R. So negative rock is greater or less than or equal to 0, -1 here, -1 for paper, -1 for scissors. The last set are just the inequality. So if you had all of your rock, paper, scissors throws, you're less than or equal to 1. You negate them, you're less than or equal to 1. And that just basically means you have to be 1. Your resulting matrix is as listed here: first 3 from the throws, next 3 from only 1 pass, and the last 2 from the equalities at the bottom. And then you transpose that into your G matrix. Let me run the C matrix here. Finally, the H matrix. The H matrix is a solution to those equations. As I stated earlier, the rock, paper, and scissors are less than or equal to 0. The next 3 are less than or equal to 0. And then your equalities are 1 and -1. And that comes from the 1 here and -1 here. So I generate the H matrix, and here I just run the solver, and the solver is from the library I imported, your C matrix, G matrix, H matrix, and the solver is the GLPX solver that I listed above, and that you'll get your result. And there's some fudging with floats, but obviously 2 to the -10 is 0 for the U, which is exactly what you want. You want that to equal to 0. And then your rock is 1/3, your paper is 1/3, and your scissors are 1/3. And that's what you'd expect because they're all equal. You throw them 1/3 of the time, and that's how you solve it. And that's my notebook, and I hope it helped with any problems you're having. Thank you.